rational maps. So, you know, if we're in a category of geometry, having introduced some objects, so I have X algebraic variety, or U, maybe U inside X, and open, let's say irreducible always. Open non-empty set, then I have these functions, rational functions k of x. So k of x, these are rational functions on x, and they're also rational functions on u. So there is a regular set. Each of these guys, each f in there has a domain, which is a dense open set in X, and so it intersects U in a dense open set of U. So each of these is a function partially, so each F is a partially defined function on X or on U. Right, and so this allows us to define a rational map. This is a definition. A rational map, for example, from X to Y. So the broken arrow there means partially defined. It's, I think in tech it's called dash arrow. So defined by F1 up to Fn, Fm. So what I'm thinking, what I have in mind, X is in a n, is an irreducible affine algebraic variety, and Y is in AM, and this map here is given by P maps to F1 of P up to Fm of P, where Fi are in K of X. Right. So there's you know, these maps are not defined everywhere. So I can, if I call this capital F, for example, a capital F is a little f1 up to a little fm, then I can write it the domain of F. So this is the open set, the dense open set, where each Fi is regular. So this is intersection of the domain of the Fi. So there's nothing surprising or difficult about this. I'm really mapping the X into AM using this F1 up to Fm, and of course I want that F1. I want that F of P is in Y for all P in X, right? All P in the domain of F, right? But so whether it's in Y or whether it's in so we map to AM in the first place. In order for it to be in Y means that the M coordinates of these points satisfy a number of polynomial equations, and so this is perfectly well defined. If they're satisfied on a dense open set in X, they'll be satisfied everywhere in X, and so we'll be home, right? And so you know, this is just an obvious definition. And we've already seen examples. So example. So when we did this. You know, when I had this circle and it's, you know, 2t over 1 plus t squared, 1 minus t squared over 1 plus t squared. This is x squared plus y squared equals 1. Right, there's some map here which is A1 with coordinate p, and it's mapping there by these functions. And it's not everywhere defined, because this is not defined where t squared is, 1 plus t squared is 0. Right, so if you're thinking of the real numbers, then you don't see these points. But I'm really thinking of always working with an algebraically closed field. And so this is, you know, there are 2 points here that they're not mapped to anywhere in this finite plane. You can think of them as mapping to infinity if you want to. Right? And, you know, you could define a map backwards if you want to. I'm not quite sure how you do it. I think you have to choose a point, and then you have to, you know, do t is the slope or something. Anyway, there's a rational map backwards. Right. So this is a rational map. This is certainly not a polynomial map. Right. The other examples we did. Let me do this example, which is sort of illustrates a point that we're going to need later in any case. So let me look at A2. This one's a morphism. This one's a everywhere regular map. Let me take this map that takes u comma v. So this is uv coordinates here. Let me write xy for coordinates there. So let me map uv into x is product uv and y is v. So if you draw, this is A2, this is the uv so this is mapping down to A2 xy. So what's happening? Maybe I want to say that one of these axes, if v is 0, the whole thing is 0. Let me just change this slightly. U and UV. Right, just to make this the picture nicer. Right. So u equals 0 is this v-axis. So the whole of the u-axis is mapped down to one point. So there's the origin there, and this origin. So this map has an inverse, right? And the inverse is only a rational map. The inverse is mapping xy maps to u and maps to x, and I want to get v from these two, so I've got to write y over x. Yes. So if I think about the map this way, then what's happening here is if I take so here's the x-axis. If I ask what happens at some fixed value of u, so this is mapping down there as an isomorphism, but it's scaled. When the u is big, it's getting stretched out. When the u gets smaller and smaller, it's getting contracted down. So if I go very, very small, then the whole length of this line is contracted down there. And then finally I get to u equals 0, and u equals 0, the whole of this line is contracted down to this point, right? And these points here, where x is 0, but y is not 0, then these points, they're not in the image of anything. There's no way of giving meaning to this y over x where x is 0 and y is not 0. Yeah? So, I mean, this is, in algebraic geometry, we often think of this as a, we think of this as a blow up, right? So I might talk about this at some in some other context later. But for the moment, what I'm thinking of this is a sort of rational change of coordinates. Right, so I've got two different copies of A2, and I'm making this change of coordinates, and so it's, you know, it's not everywhere defined. It's you know, if I'm not on this line and I'm not on this line, then you know, the map is invertible, and I'm just saying, well, I'm going to work on this little piece of the plane, and there's one set of coordinates here, another set of coordinates here, and they're affected by this contraction or expansion according to value of u, but it's just a change of coordinates. However, the change of coordinates is completely drastic at this point, where the whole line is contracted just to one point, or going the other way, at this point somehow or other gets broken up, gets expanded out to cover the whole line. So the map this way, you shouldn't think of this as a map, you should think of it as a correspondence. This point is going to correspond to the whole line. Anyway, we're not going to. So this is a. So the map. So this guy here. Let me give him a name. Let's say sigma. Sigma. And sigma is a morphism. I'm going to introduce this in just a second. It's a polynomial map. And it contracts the v-axis u equals 0 to the points 0, 0. And you know, the image of sigma is A2 minus the y-axis. Right, together with the point 0, 0. So it's a sort of pretty awkward. It's you know, it's misses out this the whole of the y-axis, but it does include the point 0, 0. Right, and so if I think about the map backwards, let's give him a name. So there's a map backwards there. Let me call him F. Right, the inverse map F is not defined on x equals 0. Not defined. There's no way that you can make this y over x regular. So you know, the coordinate ring here, x and y, is a unique factorization domain. So this expression y over x, there's no question about finding a better expression for it. This is something which is you know, not 0 at the top and 0 at the bottom. So it's not regular there. It's not defined. So you know, you can think of it making. So you can say that the point 0, 0 corresponds to the line, the y-axis. Right? If you want to think of this as not as a map, but as a correspondence, as a graph between two sets, then you can perhaps sort of think of this point together with the whole of that line. Anyway, but that's not very satisfactory. This correspondence doesn't mean anything. However, it has one strange property. This map has one strange property. This has one characteristic property, namely that this although f is not defined near 0, 0, at 0, 0, if you restrict it to a curve, let's say to an, I mean, I'm really thinking of it to the line y equals lambda x, or any non-singular curve at 0 with tangent direction not the y-axis, then the restriction is well defined. Right. So I'm saying, this is trying to consider the inverse map there. When x is 0 is obviously a pretty silly thing to do. However, let's do this. Let me write a curve here. So specifically y equals lambda x. So that's just the ordinary idea of a curve, of a line through the origin with some slope there, which is not infinity. Then this y over x is just lambda, right? And so this whole curve here is mapped up here, and it maps to x comma lambda. So it maps there to the line y equals lambda. V equals lambda. Right. So this is when you do an undergraduate course on functions of several variables, several real variables, then you learn that you can do partial derivatives, and you learn also the notion of a function of several variables being differentiable as a function of several variables, and you know that you have to be a bit careful about the order in which you take the limits. So this is really one of these things. If you take this inverse function, then it's nonsense at this point. It blows up the whole point to the line. Right? On the other hand, if you restrict it down to one little line, even though the function itself is not defined at the origin, the restriction to the line is well defined. So this is so the restriction is well defined. So the restriction has a removable singularity. Right, so as far as the line is concerned, the function looks something like lambda times z over z, which this is well, anybody sees this function and you say it's lambda if z is not equal to 0, and then there's a unique sensible way of extending it just by cancelling the z's. Right? So this is a notion of a blow up, and then this is somewhere where rational maps are happening in a completely unavoidable way. So we've seen this also. We have these maps. My favourite examples. In fact, practically my only examples in the course there's this map t goes to t squared minus 1 t cubed minus t, which you've all worked on in the example sheet. So t squared t cubed, right? And so these are polynomial maps. Right, but the inverse, they have inverses. So, you know, from C mapping back to A1, you know, given, here they're given by x comma y maps to, I don't know, x over y or y over x, y over x, y divided by x. Right, and this is a rational map. Right. So, in other words, these things called rational maps are not some kind of aberration. They're not there for a theoretical reason. They're there because you actually need them in calculations. So something that's happening here is, here I have a singular variety, and I do some operation on it, which is a rational operation, a rational change of coordinates, and I get a non-singular model. So, you know, later on, well, I'm not going to go into this in any detail in this course, but another big subject in algebraic geometry is called the resolution of singularities, and it really appears in these terms. There's this blow up, which is this strange, you know, crazy kind of change of coordinates, which is, of course, not, you know, not by well-defined maps. Here I've got coordinates u and v, here I've got coordinates x and y, and you can't write u and v as functions of x and y in as sensible functions. This is not a well-defined function, right? But nevertheless, this operation is an important part of algebraic geometry. So anyway, that's you know, to do some kind of actual examples of all the definitions. Okay, so I think I wrote down the domain already. So if you start talking about composition of rational maps, then you immediately get into problems. And one is that it can happen that a composite, you know, sort of something like f comma g is defined even at points where f and g are not defined. Right, so you know, I've got some kind of map here, f, and some kind of map g. I want to take the composite of the two because that's what you do in geometry. So you know, if you think about this example, if I map this forwards and then I map it back, then I'm mapping t into t squared minus 1 t cubed minus t, and then I'm mapping it backwards by taking x, y into y divided by x, and the effect of that is to do t maps to t, which is the identity map. And you know, it would be nice to say that the identity map is defined everywhere. And so, you know, implicitly in doing this, I'm removing a removable singularity. So if I say this map forwards followed by the map back is the identity on the t-axis, then you know, I have to do something at these two branches. These two branches map to the 2 points plus or minus 1, and you know, I'm not mapping this point back to the 2 points. I'm saying, well, we don't have to look at them, then we extend the map over removable singularities by doing this kind of trick. Right? And if you take the map, you know, I do the same thing here. I do this map, x maps to y, x comma y on the curve maps to t, which is y over x, and then map forwards, then I get the identity. And it's completely unreasonable to get the identity when the original map, to say that the identity is the composite, when the original map there is not defined. So I'm going to say that f composed with g is the identity, even though f and g are not themselves well defined. So there's a sort of crazy thing going on there. And there's something even more crazy. So it can happen that f composed with g is not defined anywhere. Right, and so you know, if I, for example, if I just want to take an example, so here's this map where x comma y here are getting mapped up to x and y over x. So you know, we can sort of live with the fact it's not defined everywhere, because we sort of give some little argument saying, well, the points where x is 0, we think of them as limits of points where x is not 0, and then we, you know, maybe we remove some singularities or something. But what happens if I take some other variety and map it in here, and the image lands entirely in this dubious locus? So it can happen. So I'm thinking here of, e.g., if you know, I've got sort of x maps to y to z. This one's called g. This one's called f. It can happen that g of x, g of domain of g, so the place where this is a partially defined map, right? And so there's some place where the domain of g, where g is a well-defined map. So I restrict myself to this big open set in x, where g is well-defined. I take g of that, right? So I end up somewhere in g, and then I want to apply f to this. So it can happen that if this thing is disjoint from domain of f, right, then g composed with f is not defined anywhere. So, you know, the thing that's happening here is that I said I'm going to do rational maps, and rational maps are not necessarily defined everywhere, and so, you know, the word rational is contradicting the definition of a map. And so, you know, this is, if you can't, you know, the category of partially defined maps just doesn't make sense, because you can't compose them. The category of partially defined does not make sense. Right, so you know, by saying partially defined maps, we're breaking one of the rules of mathematics, and we have to pay the price for it, and we get this nonsense. Okay, so there's a way around this. So the escape is to work with dominant maps, dominant rational maps. Okay, so let me explain this. So this is just a definition. I'm doing x maps to y, f there is a rational map. we say it's dominant if f applied to the domain of f is Zariski dense in Y. So you know, I'm really thinking about an example like this, where I'm going to say, well, there's these locuses. There's this little locus here, namely the v-axis, where the map is defined, but it's not an isomorphism. And then there's this map here where the map is not the inverse map is not defined at all. If we steer clear of those, we've still got Zariski dense open sets on which both the maps are well defined, right? So the thing I said earlier is if I'm mapping some variety into this space and it falls entirely into the y-axis, then I'm not going to be able to compose that map with this map upwards because it just doesn't make sense. The set of points where it's defined is empty. However, if I say, right, I'm going to take some variety and map him to this plane so that the image is Zariski dense, so that it covers the whole plane, it covers most of the plane, then this problem is not going to arise, right? So this word dominant means the image is dense. I take only the places where the map is genuinely defined, and then I take f on the locus where it's well defined, and I want the image of that to be Zariski dense. So what does Zariski dense mean? I.e., no so you know, think of this as being in AN, and this one as being in AM, right? With coordinate functions y1 up to yn. So no polynomial in y1 up to yn. Y1 up to yn vanishes on the image. So this is what Zariski dense means. I've got a subset in Y, and I'm working with Zariski topology in Y. So the closed sets in Y are defined by the vanishing of polynomials. So any closed set in Y is defined by some polynomials vanishing. So what I'm saying is that I want this image here not to be contained in any the locus of vanishing of any polynomials. And that's just the same as saying that no polynomial in the image variable, or the image f of domain of f, is not contained in any Zariski closed set. Subsets, so, you know, proper subsets of Y. So what's so good about this condition? Well, the good thing is that you know, we're working with rational functions, so we're working with the field of fractions of so you know, here I've got my x maps to y, and it's given by these you know, so let's think of this one at least as being in AM. Right, so it's given by P maps to F1 of P up to Fm of P. Right, so the y has a coordinate ring, k of y, coordinate ring, and it has a field of fractions, k of y, which is, the set of the usual thing, g over h, h and g and h, in k of square brackets y, and h not 0. Right, so this is my map F. So I'm going to say that we can define a map F upper star, a K-algebra homomorphism, F upper star from K of y into K of x. In other words, if I've got some element here, G, then I can do this is getting mapped to G composed with F. So that's what F upper star always meant. So let's just think about this. Let's just think about this. How do I define this? So how? How do I make this definition? Well, I've got K of y here, and this is just this is just y1 up to ym, and then relations. So where am I going to send the yi? I'm going to send yi to this map F, composed with taking the ith coordinates. So this is going to take, this map here is going to, the map on this level, so the F upper star on K square brackets y takes yi into fi. And the fi is an element of k of x by assumption. Like that's part of the definition of a rational map. Each of those things should be rational functions. Right? So I can do this. So now what do I have to do to be able to extend this from here up to the rational function field? So how am I going to take, so now I take, if I take some g over h in k of y, it's going to get mapped to where? Well, the thing I want to say is f upper star g over f upper star h. Okay, and these guys, so this k of y, the k of y is k of x1, y1 up to yn, y1 up to ym, and then divided out by some ideal y. Yes? So I'm this f upper star on ky is doing yi maps to fi. So if this were just a polynomial ring, well, I'm allowed to take the generated polynomial ring anywhere I like. So in fact, I've got to divide, and then iy goes to 0. Right? And that's just saying that if I take this, so because for every g in iy, g of f1 up to fm equals 0. Yeah. So when I map this map forwards, I'm mapping x forwards to y. I'm using it to take these functions, which means I'm ending up at a point in am. However, I'm at a point where I'm at a point of y, and that means all these polynomials defining y vanish there. And so this is identically 0. Right? So I have this, so I have this fy maps to k of x. This is f upper star. Okay, what do I need in order to be able to say that this is sensible? When you define the field of fractions, you're just doing sort of sensible algebraic operations. I want to map this forwards into f upper star g over f upper star h. The thing we have to check that f upper star h is still non-zero. Yes, because if I do that, then I'm just going to say, well, on this function field of y, I'm just going to map systematically every element g over h to this element there. And then you check that that's compatible with the equivalence relation and so on. Right? So why can we say this? So why? Why is this going to be true? Well, of course, in general, it's not true. However, I'm putting on this condition of dominance. So because HF is dominant. Okay? So what does that mean? If I take this guy H, he's some polynomial function on y. And so maybe he's got a locus of zeros on y. So if the whole of x where this map is defined, the whole of x maps forward and lies inside h equals 0, then the map's not dominant. So if I do f applied to dom of f, this is not contained in the hypersurface h equals 0. Therefore, f upper star h is not 0. Okay, so I introduced this notion here, dominance, and I'm still thinking of it as a geometric notion. It's saying, I'm mapping one variety there to another variety there. Here's my x, here's my y. And the image of, so, this is only a rational map. I'm thinking of the image of x here as, filling up most of y. The image of x. Where image, so f of dom f is dense in y. Right? Dense in the sense of the Zariski topology. So dense means exactly that there's no polynomial function on y which vanishes on this locus. Right? And so therefore, if I take this h and I compose him with f, I get a function on x which is still a rational function because it's a polynomial function applied to rational functions, and it's definitely not 0 on most of x. Yes? So this is this material that I'm talking about in chapter at the end of chapter 4 of the book. What I say in the book, I think, is probably fairly clear. It's I'm trying to make it I'm trying to give it some So now, now this problem, so this second problem, so if G is dominant, then G of the domain of F, the domain of G, is certainly dense, is dense in Y. So I'm mapping X to Y to Z, and so so intersects the dense open set domain of F. Right, and so F composed of G is mostly defined, and is a rational function. Is a rational map X to Z. Okay, so how do I get around this problem 1? So the point about this problem this issue here is to say that a rational map is not a, so if we have a rational map, if I have a rational map F, its domain, its domain is defined by F, so this is F1 up to Fn or whatever, not by set theory. Right. In other words, if I'm doing, do I have a sensible example of this? If I'm doing one of these, if I'm doing T maps to T squared minus 1, T cubed minus 1, and then maps to T cubed minus 1 over T squared minus 1. Right. So, where top and bottom are 0, I'm really not allowed to cancel these. So these are this expression here, this is a rational function in K of T, and K of T, and so is equal to T. It's equal to T as a rational function. So it's not equal to T set theoretically, because there are certainly points where both of these two things are 0. So I can't, this is 0 divided by 0. I'm not allowed to say that makes sense. However, it's a rational function. So in other words, first of all I make the composite as rational functions. And as rational functions, they're elements of these fields, or they're functions defined on dense open sets of the variety. I make the composite in that context, in this category of maps between fields. And having done that, then after that I decide where the map is defined. And so this is defined everywhere. And equal to the identity on A1. Right. So there's a sort of tricky point here, and a point that is very easy to ignore. It's very easy just to forget about it. So if I say that this function y over x on the line, this function y over x does not make sense at the origin or along the y-axis. So these, it's forbidden You know, the rules of logic forbid us from using this function here. So if I take, on the other hand, if I take the function, I restrict them down to this line L lambda, then it just becomes the constant. This is the line y equals lambda x. Then this is just the constant function lambda. And so then it makes sense to extend it, but notice that extending it involves cancelling numerator and denominator. It involves taking a removable singularity and removing it, removing the removable singularity. So this is the same kind of issue. So in other words, we're not worried about this. The composite F composed of G is done in the context of composing field homomorphisms, composing these maps between fields, and it's only afterwards that we ask where they're defined geometrically. Okay, so how much? What else have I got to say? What else is there in this chapter 4? Oh, okay. I want to talk about morphism. I want to talk about the definition of morphism, and in particular isomorphism. So look, I'm working here always in this context of X in AN, locus defined by polynomials. Yes? And so somewhere else there's the world of scheme theory, where I have X, OX, and so on. So I have some kind of slightly more abstractly defined varieties, but they're still varieties in my sense, or the varieties in my sense immediately give examples of these things. And then there is this sheaf of functions, which are the locally defined regular functions, right? And so in this theory you have a notion of a morphism. So I want to tell you what the notion of morphism is in my setup. So if U in X is an open set, then a morphism U2. So let's have V in Y open set also. Right, a morphism U to V is a rational map X to Y such that, so I want it to be defined everywhere. So I want U is contained in the domain of F. So let me call this F. U is contained in the domain of F, so that the map is defined everywhere, and F of U is contained in V. So I'm just saying I have this language in which sometimes you have to write down maps that are only partially defined. Now I'm going to try to repair that language by introducing this word morphism. So this is a morphism is a rational map which is everywhere defined. So whenever you have now we have a category where the objects are varieties V, varieties, let's say U. So implicitly here U is open in an irreducible affine algebraic variety. We'll have to do a bit more work later to get this, but this is already a big start. and the maps are morphisms. Right, so I told you what a morphism between two of these quasi-affine varieties is. Yes. So whenever you have this, so now we have this. Now we have this proper, category where I've told you what the objects are, I've told you what the maps are. Then it's automatic that we get an isomorphism. Right. So no surprise here. An isomorphism. It's a map it's a morphism U to V with having an inverse G. Right. So it's a morphism with an inverse morphism. Right. So there's my morphisms are defined in terms of rational maps. So there's something slightly crazy going on here. But I'm just saying, well, we do the sensible thing of allowing rational maps here and all of the stuff that comes with rational maps when I'm mapping between varieties. But when I say morphism, I insist that the place we're looking at, the map is everywhere regular. Right? So this means, of course, that f from U to V is morphism, and that's G from V to U, likewise, and that U composed, whatever it is, F composed with G and G composed with F are the identity on wherever this makes sense, right? So G composed with F goes first I do G and then I do F, so this is the identity on U. Identity on V, and this is the identity on U. Right, so examples, well, there are already two examples on the board there. Right, so we've already known, we always know that, if you want even set theoretically, you have to exclude these points from consideration. There, one way or another, the maps are not defined or the maps are not one-to-one. Right, so I say, example, we'll see we'll see more of this in more complicated examples, but I'm taking A1 minus the 2 points, t equals plus or minus 1, and I'm mapping to C minus the origin, so this is, what's this one? Y squared equals x cubed plus x. Have I got this right? X squared plus x squared. Right? And this is an isomorphism. Okay, so as you know from what Young Nam said, I'm going to be away for next week, and then the next lecture is Tuesday the 25th in 10 days' time. And I hope to see you at